Right, we're starting out here with an analysis decision flow chart. As you guys saw on exam 2, it's very important to make sure that you are using the proper approach to solving the problem. So far, we've been working in our sections here with the Z distribution table. Since we worked with it chapter 6 a lot, this is if our sigma is known. So if we know the standard deviation for our entire population, and our population is normally distributed, or we have an n greater than 30, then we use the Z normal distribution, which we've been working with so far. However, now we're going to start looking at using the T distribution table. Now, this is if the population is normally distributed or the n is greater than 30, but we do not know what our standard deviation is for the overall population. If this is the case, we use the T distribution. We're going to be looking at that here in terms of estimating a population mean, and then in chapter 9, we're going to be looking at t-test comparison of means. So let's take a little time to get used to this T distribution table. This was developed by William Gossett, who was responsible for quality assessment at Guinness Brewery. William Gossett was doing quality assessment and acceptance sampling, much as we looked at before, and needed an approach that he could use when he did not know what the actual overall standard deviation of the population was, but did have a standard deviation for specific samples. So he developed the T distribution table, version of which you see over here on the right. He published it under the name of Student because at that time Guinness Brewery did not allow their researchers to publish any of their work. So if we're going to use our T distribution table, first we need to know the direction of the analysis we're solving for, whether we're looking for a one-tail or a two-tail. So as we go along, we're going to come back to that in just a few minutes and take a look at that in greater detail. But keep in mind here, unless it's otherwise specified, we're going to be looking at a two-tail. Now, here's the difference we have. So here on the right is the two-tail. This means you're looking at a value both to the left and the right of the mean. Okay? I use two t critical values, both a negative and a positive. Over here on the left, you can see the images of the one-tails. Here we have our critical value t would be to the left or a negative, and our critical value t would be to the right or positive for the right tail. So if we look at this, you'll notice that the alpha for both of these, if we're looking at the one tail, all resides completely in one side. So all of alpha is either to the left of the t critical value or all of alpha is to the right of the t critical value. If you look over here at your two tail, you'll see that that is different. Here, the alpha is divided into two. Now, when I'm talking about alpha, what do I mean by alpha? I'm talking about when we're looking at, if you have a confidence interval, for example, of 95%, and you're solving for, you have set your value as 0.05, that 0.05 is your alpha. Okay, so if we take a look here, see if we have an alpha of a 95% confidence interval will be 0.05. That full 0.05 would reside either to the left of the t critical value or to the right. Now notice in the t distribution here, the critical values do not sum from the left as they did with the z distribution table, but we do have to be careful here looking if we have a one tail or a two tail, which is a factor we did not have to look at with the z distribution table. So using the two tables, we have to use them differently. All right, so if we look over here at our two tail, we can see we have our 95% confidence interval, which equals a total alpha of 0.05. But because it has to be on both sides, it has to be divided by 2. If I have 0.05 to the left of my negative t critical value and 0.05 to the right of my t critical value, then when I sum those two 0.05s, I would actually have 0.10, which would correspond to a 90% confidence interval, not the 95% I've been asked to solve for. Now, the t distribution table does this for you. So here you can see, if you're looking at this, we have the area in the two tails is doubled that of the area in the one tail for this corresponding degrees of freedom. Okay, so if we go across here and we're looking, so you can see the area in the one tail is 0.025, right? And for the two tail, it's 0.05. That's 0.025 times 2 equals 0.05. So, for example, if we followed our degrees of freedom 6 here on the left, we follow this across, we're going to see that the t critical value for a two tail at 0.05 is the same as the critical value for a one tail at 0.025. So if you need to, take a few minutes, pause the video here, go through and make sure you're familiar with how this part of the t distribution table works. Some students find it very helpful to block off the top part of the area of 1 tails and basically convert it into a table of only 2 tails and photocopy that, and then reverse that and block off the section that says area of 2 tails and photocopy it to produce a table for area 1 tail only, so you don't make mistakes. If you find that helpful, I recommend you do that. If that's the only thing between you and getting the answer correct, then those 2 photocopies can really be a lifesaver for you. Okay, so let's go back here to our t-distribution table. So here we've got, we're going to look at this with the area in the 2 tails, since that's the most common we'll be looking at, especially if we're doing a confidence interval. You've got to have a value on both sides. Now the next we need is the alpha level. And so as we just looked at, if we have a confidence interval of 95%, 1 minus 0.95 gives us an alpha of 0.05. So we're going to start off whether or not we're in a 1 tail or a 2 tail. Then we're going to locate our alpha level under the correct table section. And then the last thing we're going to do is look at our degrees of freedom. So our degrees of freedom here, n minus 1 is going to be our degrees of freedom. So if we had an n of 7, it would be 7 minus 1 equals 6. Okay, and we come down here, you can see the blue arrow. That is the column for the degrees of freedom. So solving for this particular example we have here, I would have my area in my 2 tails, come down with my 0.05 for my alpha, and then across for my 6 degrees of freedom, and my t critical value here would be 2.447. Take a few minutes and make sure you go through that and you follow how you would apply that yourself for locating a particular t critical value for a problem where you are given the directionality of it, whether it's directional or non-directional. And again, you would assume it's non-directional unless told otherwise, with a specific alpha level that you compute from a confidence interval, and your degrees of freedom as you compute from your n. Okay, now let's look at a couple of properties of the student t-distribution. So, first of all, it is different for each sample size. So this is very different than our z-distribution table. We had one distribution for all cases. Here we are looking at, depending upon our n size, we're going to have slightly different distributions. So they're all going to have the same bell-shaped curve and normal distribution, but they're going to have a wider distribution or variability with the smaller sample sizes. So if you look here in this example, you can see that the distribution for n of 3, the yellow line, is wider than the n of 12, which is the red line. We can see that both down here at the bottom in the spread, and also you can see it up at the top part where the distribution peaks. Notice that that's actually when we're looking at that there. Okay, so the peak there for the n of 12 is a little bit higher. That means that our mean is occurring more frequently. So as the sample size gets larger, this gets closer to a standard normal distribution. Again, you can see here comparing the n of 3 with the standard normal distribution that's shown in the shape in the blue. And we notice as the n gets up larger, for example, the n of 12 and the red line is closer to the standard normal distribution shape than the n of 3. So when we're looking at the student t distributions, keep in mind we always have a mean of t equals 0. We're going to have a standard deviation that's going to vary with the sample size, which again is very important, but it's always going to be greater than 1. So remember, with the standard normal distribution, we had the standard deviation for the population was equal to 1. Here we're looking at the standard deviation with a sample size, and it is always going to be greater than 1. Now, notice when we're looking at how the shape of the distribution changes, this is due to your central limit theorem. So, if you remember going back and looking at the central limit theorem applets that we had you run in the previous section for 6.5, and looking at how those distribution shapes changed as your n size got larger, this is exactly what we're seeing here with the student t distribution. So if you need any clarification with that, I suggest you go back and do that particular video again and go through those applets again so you can see for yourself the central limit theorem in effect.